Hi everybody, welcome to lecture number 20, video number 1. This is all about biomass. We're only going to spend one day here. Wish we could spend more time. Alright, so as usual we're going to spend our first video talking about the resource, the biomass resource. In order to do that, let's define exactly what biomass is. So biomass, we're going to say, is energy that we are deriving from we'll say not living matter, but recently living matter. When you're burning a plant, I don't think it's alive anymore once you're done burning it. Okay, so we're saying recently living matter because what we're trying to do is differentiate biomass from fossil fuels. In reality, fossil fuels is also biomass, right? However, it's biomass from millions of years ago. In this case, we're trying to say biomass is chemical energy stored in the bonds of something that was living recently. Okay, and just like almost any other renewable energy resource, biomass is not the beginning of the energy. That energy came from somewhere, and of course it is the sun. Biomass is really solar energy. As a bonus, it's stored solar energy. Like hydropower, biomass is a very convenient energy method that allows us to store solar energy and use it on demand, as opposed to solar panels, photovoltaics, which require that energy to be available at that moment. So a very useful resource and undoubtedly a mix in the future energy generation mix. Definitely a contributing part of the energy generation mix in the future of this world. Okay, but how do we take the sun and turn that into a tree? Those are obviously not the same thing, right? That's where photosynthesis comes in. I'm sure we've all heard of photosynthesis, right? Which is actually, turns out, a very complicated process in which solar energy is ultimately converted into chemical energy. So we're going to write out a chemical reaction here. If we take 6 units of carbon dioxide and combine it with 6 units of water, and then we need to add some energy in the form of light. So if we add some energy to CO2 and H2O, we yield this new compound C6H12O6 and some oxygen. This larger compound here is glucose, or just a sugar, and think of it just as chemical energy. In this reaction we used carbon dioxide and water, so here's our plant, right, and it's got leaves. It's taking in carbon dioxide and sucking up water through its roots. These meet at the leaf where sunlight impinges. As soon as that happens, then we release some oxygen, and that leaf then grows a tiny bit. That's the glucose. That sunlight is stored as chemical energy as glucose. Now there is a lot in this arrow right here. There are many intermediate steps. Specifically, as soon as sunlight hits, it doesn't convert that sunlight directly into glucose. It actually changes it into the energy carrier of the plant, kind of an energy currency, which that plant uses right away if it needs it. If there is excess, and only if there is excess, then the plant uses that to create glucose and grows, right? So really, solar energy is only stored when the plant isn't using it. So only when a plant is growing are we storing solar energy. Oops. Okay, so our global energy capture, the amount of solar energy that we are kind of storing, amounts to about 130 terawatts. So at any moment we're capturing 130 terajoules of energy per second, which is great. That's about 8 times human consumption. Okay, and this generates well, this captures and stores 100 million tons of carbon every year. All that carbon in the atmosphere is converted into plant material. Okay, but let's talk about some of the things about photosynthesis we don't always hear about, specifically how inefficient the process actually is. So before we can learn about that, we have to learn about photorespiration. Okay, so you see here in this chemical reaction, we need a specific amount of energy so that the energy at the end of the reaction and at the beginning of the reaction are equivalent. Now, that means we need a certain amount of CO2 and a certain amount of water. However, if the available light, so if there's a lot of light and maybe not a lot of CO2 in the air surrounding the tree at that moment, then the plant photorespires. So what it does is it actually runs this process in reverse. It does the opposite, and it consumes energy in order to preserve the plant. So if there's excess energy, just like if you're outside and it's too hot, you're going to sweat in order to keep yourself at the correct temperature. A plant, if there's excess energy, will be damaged. It consumes that energy by consuming some of its stored glucose in order to create, once again, CO2 and H2O. And it takes that energy to break apart these bonds, kind of using that energy and preserving the plant. Now, there's only a certain class of plants that use this. We call them C3 plants. Use photorespiration in order to be preserved. However, there are a different class of plants called C4 plants, which are kind of more native to the equator, where the amount of light is more constant than up here in the temperate zones. These plants actually store carbon dioxide in their leaves. Because they do this, they never have to photorespire, so they never have to do photorespiration, which means they are more efficient. They don't have to consume some of their sugars in order to stay alive when there's too much light. All right, so that brings us to the topic of photosynthesis efficiency. Just how efficient is this process? We always think of nature as being the ultimate at producing, the most efficient processes. So this has to be so crazy efficient, right? Well, nature doesn't care about efficiency. The only thing nature cares about is providing the energy it needs with the resources it has. What this means is that the way we consider efficiency, photosynthesis is about 0.05% efficient. That's right, this decimal is supposed to be there. It is 0.5% efficient, which means if we have a field and if we add up the total amount of energy that hits that field over a year, and then if we track how much chemical energy was added to this plant over a year, we will find that the amount of energy added to that plant is 0.5% of the total amount of energy that was hitting that field. Okay, so let's talk about why that is. So first, the biggest one is only 12% of light hitting a given square. So let's just say a field filled with plants actually reaches growing leaves. Remember, we talked about if a plant isn't growing, it's not storing energy. And so this means that for only a few months in the year, a plant is going to grow, which means the sunlight hitting any other time of the year is wasted. In other words, not used to produce chemical energy. So only 12% of that light that falls on a field is going to hit a leaf that is growing because of time and because of the actual geometry of the leaf. Some might hit stems, some might hit the roots, some might hit the stalks. Not everything hits the leaf. So that's a pretty big ding right there. Okay, another problem is, just like with photovoltaics, only 50% of the radiation is usable. It needs to be in the correct wavelength range. Remember, we talked about reaction energies. Our photon must have enough energy in order to make this reaction occur. There are many photons in light that don't have enough energy, so only 50% can be used. Okay, on top of that, only 85% of that radiation is absorbed. Our leaves aren't perfect. They reflect away some of the radiation that they could have used. Okay, then there's the actual efficiency of the process. Remember, not everything is converted into glucose. Some is converted into a plant's energy currency molecule, which is then used right away. So only 20% is converted into something like glucose. And then on top of that, you hit the summertime and there's way too much light for the amount of CO2, which means 40% of the glucose you made is lost in photorespiration. Add all of these up, well, multiply all of these up, and you get 0.5% efficient. Again, nature doesn't care about efficiency. It just wants to know, can I keep growing? And plants still grow, so it doesn't really matter. All right. Now, that's about photosynthesis, but that's only a part of the game. A tree is not useful to us unless we can use that energy, right? So how are we going to utilize the energy that is trapped inside of a tree? That is through the process of combustion. So let's review some combustion. All right, so we have methane, CH4, the smallest hydrocarbon. If it is in the presence of oxygen, and if we heat the methane and oxygen to the appropriate combustion temperature, then a lot of things are going to happen at once, which we summarize with an arrow. But there's intermediate reactions occurring here. When you light a fire, you see there's a variety of colors. A lot of things are happening in that flame that are changing CH4 and oxygen into a variety of intermediate components. But eventually, once it's all said and done, you are left with carbon dioxide and 2 units of water plus some energy, right? So if we look and add up the total bond energy, so the energy inherent in the bonds holding these atoms together, and compare it to the total bond energy holding these atoms together, then we will find that the bond energy of CH4 and oxygen is greater than the bond energy of carbon dioxide and water, quite significantly actually. We can quantify the fuel heating value, which is the amount of energy released per unit mass. This is a convenient way of comparing fuels, right? Because this is one hydrocarbon. There are a variety of hydrocarbons, sugars, and alcohols that we can actually put in oxygen and combust. They all release a different amount of energy. Okay, just some quick notes about combustion, some interesting things. First, let's talk about oxygen. The oxygen bond is actually the key to combustion because the O2 bond is naturally unstable. It doesn't necessarily like being put together. It wants to be torn apart. And a hydrocarbon is almost like a key, ideally suited. Really any organic compound is ideally suited to tear apart oxygen if given enough energy, reaction energy to do so. Also, oxygen has significant bond energy itself. Really, when we talk about combustion, not all of the energy is stored just inside the hydrocarbon. We're not just releasing energy from here, we are also releasing energy from this bond. And both of those bonds breaking is what contributes to the total amount of energy that is being released. So, depending on your hydrocarbon, you need different amounts of oxygen. The more oxygen you need for given for a given mass of hydrocarbon, the more energy you're going to release. Okay, but let's not shortchange the hydrocarbons or any organic matter. They have very high bond energy. Perhaps just the highest bond energies we can find. They're ideally suited to be energy carriers, which makes sense, right? This is organic matter. It was collecting energy its whole life, and it had to store it the most efficiently. Okay, and we've already talked about how there's a combustion temperature, right? If you just leave a gallon of gasoline in the open, nothing's going to happen. But if you light a match and heat some of the oxygen and fuel to a given temperature, then a reaction will occur. Then, of course, it's a chain reaction, right? As soon as one reaction occurs, then it heats the air around it, and all of the other fuel begins to combust, and you have then an explosion. Let's see. Looks like I put this slide a little too early. That's okay. So we're just going to erase some of this right here and talk about some combustion inefficiencies. We can just do it right here. Okay, so not all fuels are equivalent. There are some things about certain fuels that make them not exactly ideal as a fuel. So let's write our reaction again for methane, natural gas. Okay, then we're going to write our reaction if we were to combust this glucose. Really, we're just going to write this entire reaction in reverse. Let's see, so right here. So here's our glucose. And that is combusting with oxygen and forming carbon dioxide and water. Now I want you to notice some things. Number one, the most important, look at what is in our fuel. So here, with methane, we just have carbon and hydrogen. Here, with glucose, we have oxygen inside of our fuel already. Let's see what that does. So here, our methane has 6 times more carbon. However, it has only 3 times the amount of oxygen in the combustion reaction compared to methane. Remember what we talked about, how oxygen contributes energy as well. Because some oxygen is already inside of our fuel, you don't need as much oxygen for your reaction. What this means is that the amount of energy released is less per unit mass of fuel. However, we still release 6 times the CO2. So we get less energy and we generate essentially 6 times as much CO2. So the amount of carbon dioxide released per unit energy is significantly higher when we have oxygen in our fuel. Okay, so that leads to some kind of rules of thumb, which is that, fuels with oxygen are less ideal. My combustion professor described them as half burned already, right? Half of those carbon-hydrogen bonds have been taken by oxygen already. It's half burned. Okay, coal and biomass have oxygen in them. So right away, that's a ding. Okay, next let's talk about water. So if we have water in our fuel, not in the fuel itself, like not in the methane, but mixed in with our fuel, that reduces our combustion efficiency. And that's because the water must be heated and evaporated, which takes some of that energy that we had stored. Instead of releasing it as thermal energy, it is used instead as latent energy in this water. So as an example, let's look at this table right here showing fuel and the energy content in that fuel. Let's switch to a different color. Okay, so here we've got wood, green wood. So at 60% of the wood is moisture. Our energy content is 6 gigajoules per ton of that wood. This is the heating value. Now if we dry that wood and remove that water, we get 18, 3 times the amount of energy just by taking out the water. That's pretty cool, right? Okay, let's look at some other interesting values here. So like fresh cut grass, which is going to be pretty wet. It's a very small number compared to dried dung or newspaper. Or charcoal, which is, we're going to talk about charcoal, is a pretty high value. But the real king is natural gas at 55. The amount of energy per ton is great because, again, look at CH4. There's nothing in there but a carbon and hydrogen bonds. And those are all unlocked by oxygen, and you use the most oxygen per unit mass of fuel. It's amazing stuff. Compared with coal, which is half that value because, again, it is half burned. Okay, that is our discussion for the resource. Next, we're going to talk about technology.